Imagine your bedroom lifted gently from its floor and carried in a slow, silent circle around a pale blue marble. The lamp, your book, the familiar dent of the mattress, all of it is traveling together. And yet inside your little bubble, the usual sense of down has loosened like a knot. Welcome to Gravity Unplugged. Before we drift too far, make yourself comfortable. Arrange your head, let your shoulders unclench, and let your breathing find its own soft, steady rhythm. If you enjoy this kind of quiet, curious wandering through the cosmos, a small favor. If this finds you, like the video and subscribe for more gentle explorations. That helps me keep making these late-night voyages for you. What we're doing tonight is simple and a little odd. We'll use the experience of floating, of apparent weightlessness in the quiet vacuum outside Earth, to learn about gravity at every scale, from the apple that nudged a thought into being centuries ago to the way entire galaxies cuddle together across cosmic time. Gravity is both more ordinary and more mysterious than it looks. And the paradox that makes the best bedtime companion for a scientist is this: sometimes the best way to understand something is to step back and feel its absence, or at least its absence as we usually expected. When astronauts float, gravity hasn't gone on holiday. It simply played a subtler hand. Let's start, as many stories do, with the apple. The tale of Sir Isaac Newton and a falling fruit is a comfortable piece of folklore. Whether an apple actually bonked his skull is beside the point. The image is useful. Newton pictured gravity as a force. Masses attract each other. The bigger the mass, the stronger the pull. Put a bowling ball and marble on a sheet, and the bowling ball settles down. The marble rolls inwards. This is a simple way to imagine how mass draws objects together. In Newton's way of thinking, you could measure the pull, you could predict how hard it would tug, and you'd get delightfully accurate answers for most everyday affairs: projectile motions, tides, the paths of planets. A couple of centuries later, Albert Einstein invited us to think differently. He said, "What if gravity is not so much a force as a feature of space itself? Picture space not as empty nothingness, but as a gently stretchy fabric. Lay a heavy ball on that fabric and it sags. Roll a smaller ball nearby and it spirals inwards, not because of an invisible tugging hand, but because the fabric guides its path." In Einstein's general relativity, mass and energy tell space how to curve, and space tells objects how to move. The effect is the same in many situations. Planets still orbit, apples still fall, but the language changes from pulling forces to geometry. Both descriptions are useful. Newton's law is the comfortable calculator for a ball thrown in a bark. Einstein gives us the language to talk about light skimming past the sun, or clocks ticking slightly differently at different altitudes.
Practical life even relies on this correction. The satellite clocks in GPS systems need adjustments that come from relativity. Without them, your navigation would wander by several meters each day. So we carry both pictures with us: force when it helps us solve a problem with simple arithmetic, and curved space when the problem grows more subtle and precise. Now, imagine you aboard a small capsule high above the ground, windows seeing a round horizon you can learn to recognize. Earth's pull is still there. At about 400 kilometers above the surface, roughly where the International Space Station orbits, the gravitational pull is only a little weaker than at ground level. The reason astronauts float isn't that gravity disappears, it's that they are in continuous free fall. Think of an elevator with its cables cut in a movie. Everything inside would fall together. For a short, dramatic time, you would appear weightless as you, the chair, and a floating pen fell at the same rate. Orbital freefall is the trick played in slow, graceful motion. The station is hurtling sideways so fast, about 28,000 kilometers per hour, that as it falls towards Earth, the planet's surface curves away beneath it. The station keeps missing Earth, so it keeps falling around it, tracing an endless arc. Inside, everything shares that fall. You, your toothbrush, a tumbling pen. From your perspective, it feels like floating. That sensation is paradoxical. You might expect that leaving the ground means leaving gravity behind, but instead you enter a state where gravity is the silent director of motion. Your body no longer pushes against the ground, and without that contact, certain everyday cues evaporate. The inner ear, which senses orientation through fluids and tiny calcium crystals, no longer has the constant pull of down to report. The fluid in your veins redistributes. Meals behave differently. Small things that on Earth stay put suddenly drift with a polite independence. Let your imagination roam there for a moment. Picture a pen released from your fingertips. It doesn't fall away. It lazily holds its place relative to you. A cup of water will not obediently sit on a table. Instead, depending on how you handle it, the water may cling in soft spheres to the cup's rim or suspend in beads in midair. Bread behaves differently too. Tortillas, with no crumbs to launch into orbit, have become a favorite on the station because they are less likely to cause floating particles. Replace your mental plate with a foil pouch of stew and a straw. Many meals up there come in squeezable pouches or are rehydratable pouches you pinch and sip. These small details tell you how little rituals of gravity are woven into our daily life. At this point, you might be asking, what happens to our bodies when these rituals are rubbed away? The body is a structure evolved under the steady pull of Earth. Remove that constant mechanical load, and it slowly begins to rework itself.
One of the most immediate changes is what we call fluid shift. On the ground, gravity helps pull blood and fluids towards the lower limbs. In microgravity, those fluids redistribute upwards. Astronauts often describe puffy face bird legs. The face looks fuller, the legs relatively thinner. This is a benign-sounding change, but it is connected to deeper physiological cascades. For some crew members, the fluid shift contributes to discomfort, headaches, and changes in vision over time. There's a particular condition that has gathered attention in the space medicine community, spaceflight-associated neuroocular syndrome, or SANS. It is a cluster of changes that can affect eye structure and visual acuity, possibly linked to fluid movement in the skull and changes in intracranial pressure. Scientists are still learning which astronauts are most susceptible and why. It's not a simple story with one guaranteed outcome for everyone, and that uncertainty is important to hold gently rather than alarmingly, but it is one of the puzzles that remind us spaceflight is not merely romantic gazing at Earth, it is a physiological experiment in slow motion. Muscles and bones also respond to the lightness. Bone is a living tissue that remodels itself in response to load. On Earth, our skeletons are constantly subjected to mechanical stress from walking, standing, and gravity's tug. That stress tells bone to maintain density. In microgravity, bones are underused and begin to lose mineral density. The numbers are striking enough to matter. Studies suggest astronauts can lose around 1 to 2% of bone mineral density per month in certain regions, particularly weight-bearing bones. This is why regular, often intense exercise is not optional in space, it's medicine. Resistance machines and structured routines aim to mimic the stresses Earth provides, at least enough to slow the loss. The recovery back on Earth is possible, but can be lengthy, and the long-term consequences are still something researchers watch closely. Muscle atrophy follows a similar logic. Without the need to stand, to climb stairs, to haul a loaded shopping bag, some muscle groups relax their grip on the world. Astronauts spend hours each day on exercise devices, running on a treadmill strapped in place, pulling against elastic or pneumatic resistance machines that try to simulate weight. It is worth pausing to picture those machines, bulky, mechanical, and strangely domestic inside the station, because they are among the quiet heroes of long-duration missions. They are not glamorous, but they are essential. Beyond physiology, there is the vestibular surprise. The inner ear expects gravity to give it a reliable vector. Remove that vector, and orientation becomes a softer thing. New crew members often experience space adaptation syndrome, nausea, disorientation, a sense of movement when still.
It usually passes as the brain adjusts to the new sensory environment, but the first days can be uncomfortable. One of the small ironies of life in orbit is that astronauts, who spend their lives training in simulators and rehearsing critical tasks, can be humbled by a tumbling toothbrush. Psychological impacts are also part of the ledger: isolation, confinement, separation from family and daily routines, and the blur of day and night. The International Space Station, circling Earth roughly every 90 minutes, sees 16 sunrises and sunsets in a single day. That rhythm doesn't do wonders for circadian cycles, so crew members often use scheduled lighting and sleep routines to anchor themselves. Yet many report profound psychological gifts as well: a stronger appreciation for home, a sense of awe at the fragile color of our planet, and the calming ritual of watching storms or city lights roll by in a thin, luminous band. Life aboard the station is an artistry of small solutions. Let me paint some of those everyday adaptations with a few household images so you can feel the choreography. Meals. Food often arrives as thermostabilized packets, rehydratable pouches, or squeezable tubes. There are bite-sized dishes marshaled with Velcro. That little patch of fuzzy hook and loop is an astronaut's best friend. It secures objects against the tendency to drift. You may laugh, but Velcro is to a spacecraft what cupboard doors are to a kitchen, both a constraint and a convenience. Sleeping. Instead of a bed that bears you down with springs and gravity, astronauts sleep in sleeping bags tethered to the wall or in a small private sleep compartment. The bag is anchored so that the sleeper doesn't drift and bump their head against a ceiling fan or equipment. Some crew members prefer to strap their feet down so they don't float away mid-snooze. In the absence of a firm mattress, these choices become measures of comfort and security. Hygiene. Running water in a shower is a deluge that would make every drop float as a bead. So hygiene is mostly done with rinseless wipes, no-rinse shampoos, and carefully managed rinses where water is captured and filtered. Even the toothbrush routine is adapted. Toothpaste is usually put on the brush and swallowed or wiped away rather than rinsed in a stream. Habits that on Earth feel automatic must be deliberately choreographed. Sanitation. The toilet on a spacecraft is a marvel of applied pragmatism. It uses airflow, suction, to guide waste into containment. Every drop of water is precious and part of a highly engineered recycling system. The principle behind these systems is humility before resources. On Earth, we take inexhaustible water for granted. In orbit, closed-loop systems recycle urine into potable water after rigorous purification. It is not poetry to say that in space, yesterday's water quite plausibly becomes tomorrow's coffee.
Movement. Handrails, foot loops, straps, and Velcro combine to make mobility predictable. Foot straps allow you to anchor yourself while working. Handrails provide steady points of reference while you maneuver through a cramped corridor. Teams choreograph work like a quiet, efficient dance. Even mundane tasks, passing a wrench, opening a storage box, become rehearsed sequences to avoid the comedy of floating tools. Now, let's breathe into the implications of all this. What does floating teach cosmology? Or rather, what can the microgravity experience reveal about gravity itself? The first lesson is humility. When you experience weightlessness, you feel the absence of a tactile normal. This absence forces you to ask which of the phenomena you took for granted are truly fundamental, and which are artifacts of living in a particular environment. Gravity, it turns out, is an organizing principle that works at every scale, but with different languages. The apple that drops and the galaxy that holds itself together are answers to the same fundamental script, but written in different fonts. The second lesson is clarity about mechanism. When astronauts float, we understand that they are not escaping gravity's influence. Rather, they are following geodesics, natural, straightest possible paths in the curved geometry shaped by Earth's mass. This phrase, geodesic, is the kind of technical word that can seem sterile. It simply means the route an object takes when it's not being pushed or pulled in any direction except by the shape of space itself. In practical terms, orbital motion is the body's comfortable response to the curvature of spacetime created by a planet the size of Earth. Third is an appreciation for scale. The same force of attraction that brings a pen into your hand and a fruit to the ground, when aggregated and distributed across countless tons of gas and dust, sculpts stars. In a cold molecular cloud, tiny fluctuations in density can tip a region into collapse. Gravity pulls material inwards, heating and compressing it until nuclear fusion ignites and a star is born. On vastly larger scales, gravity molds galaxies and binds them into clusters. Cosmologists map a cosmic web with filaments and voids, the scaffolding on which galaxies assemble. There is a compositional elegance in thinking this way. Gravity acts patiently, over vast distances and unhurried times. It is neither dramatic nor dim. It is a longhand sculptor. And yet, when we push the concept to extremes, it raises profound questions. What exactly is the relationship between mass and the curvature of space? How does gravity behave where space-time becomes very steep, near a black hole, for instance? How should we think about the extra gravitational influence we infer from galaxy rotation curves, something we call dark matter, or from the accelerated expansion of the universe, which we often label dark energy?
These are not the urgent questions of a sleeping mind, but they are the gentle, persistent curiosities that keep scientists awake in the best possible way. Before we drift on, one practical image will help ground what I'm saying. If gravity were a melody, microgravity is not silence, but a change in key. The music continues, the tempo shifts, and reveals harmonies you couldn't hear before. Observing how systems respond in that changed key, how human physiology remixes, how fluids reconfigure, how combustion behaves differently, offers insights not only into the nature of gravity, but into how life might adapt to environments beyond Earth. In the next chapter, we'll look more closely at the ingenious devices and engineering designs that make prolonged life in microgravity possible. We'll visit the treadmill strapped to a frame that keeps an astronaut grounded by elastic force.
we'll consider the air circulation system that quietly shepherds odors and floating crumbs away from delicate instruments, and we'll discuss how rescue and safety systems account for gravity's reappearance at launch and re-entry. Briefly, the times when gravity stops being a whisper and starts to roar. For now, let that image settle. You in a sleeping bag, tethered to a wall. The world outside a slow parade of blues and greens. You are in continuous freefall, circling a planet whose gravity both loosens and defines you. As you breathe, notice how your chest rises and falls without the familiar counterpoint of the floor beneath you. Let that paradox, absence and continued influence, sit like a soft orbit in your mind. There is one more human angle to cover before we turn the page to the machines. Astronauts often speak of a subtle recalibration of values after spending time aloft. The trivialities of daily life on Earth sometimes seem to rearrange themselves into new priorities: the warmth of a shared meal, the odd consonants of a family member's laugh, the sight of a coastline curving like a memory. From space, borders blur, and color bands of weather and light sharpen. This perceptual reorientation is not trivial. It feeds back into science. Observations made by people who live with this perspective, who can point to a storm and name its system, often lead to surprising, human-scale questions. We will carry this human note into our next part, where the engineering and the machines meet the biology, and where the quiet choreography of life aboard the station reveals how deeply our species depends on both cleverness and caution. For now, allow your shoulders to relax. Imagine the pen floating gently away from your fingers, pausing, then drifting back as if summoned. Notice the way the world feels a little less anchored, and let your curiosity drift with it. Let your shoulders go a little softer as we move from the human note to the quiet machinery that makes this suspended life possible.
We've already seen how bodies rearrange themselves when the everyday tug of the planet is no longer the constant backdrop. Now imagine the station itself, an intricate ecosystem of pumps, fans, filters, and routines, working like a slow, attentive household that must never forget a single task. In that world, engineering is not merely technical, it is a kind of hospitality, an ongoing promise that the small comforts of life will continue despite the absence of a floor. Air is one of the simplest examples, and one of the most vital. On Earth, a gust outside or a window left open will exchange air in a room without much fuss. Up there, any stray crumb, perfume, or overheated circuit could become a persistent nuisance if not managed. The station relies on continuous ventilation, fans that gently move the air through filters and past sensors. These systems are designed to avoid pockets of stagnant air where CO2 might build up, or where floating particles could gather around delicate instruments. The airflow is engineered to carry debris into the filters, to guide exhaled breath into scrubbers, and to shepherd odors and aerosols away from sleeping compartments and controls. In the quiet hum of those fans, the station breathes. Water recycling is another quiet miracle. You might imagine a cascade of water and waste into a down-the-drain oblivion, but there is no infinite sink in orbit. Instead, every drop is a resource. Gray water, condensate from air conditioning, even urine are channeled into purification systems. Filtration, distillation, and chemical treatment are used to yield potable water again. It's an elegant humility. In a place where mass and volume are at a premium, the simplest comforts are reclaimed. The success of closed-loop systems is not only an engineering triumph, it's a cultural one. Astronauts learn to treat water with a different respect. A sip is never wasted. Exercise equipment deserves a longer look because it is the medicine of long-duration missions. Without gravity, you can't simply stand on a scale to measure your work against the world. So engineers designed machines to impose a load artificially. There are resistive devices that mimic the effects of lifting heavy weights, using vacuum cylinders or flywheels to provide a steady opposition. The treadmill, a familiar sight even in the narrow corridors of the station, uses harnesses or bungee cords to keep feet in contact with the running surface. These devices are heavy and oddly domestic-looking in the cramped modules, but they are the principal defense against bone and muscle loss. Spacesuits and emergency systems are the safety net that accepts the responsibility for the rare but consequential moments when the station's soft hush gives way to urgency. A suit used for an extravehicular activity is a miniature life support system. It provides oxygen, removes carbon dioxide, controls temperature, and offers some radiation protection.
For astronauts working outside the station, tools are tethered and movements rehearsed. A stray push can start a slow, relentless drift. There is also a small but elegant rescue device for those rare untethered moments, a compact propulsive backpack that can offer short bursts to return an astronaut to the station. The very existence of this gear is a reminder that while microgravity allows calm movement and slow discovery, it does not eliminate the need for contingency. Even mundane items, Velcro strips, bungee cords, foot loops, and handrails are the unsung choreography of daily life. They are the improvisational grammar by which people move, work, and eat. Storage is carefully designed so that nothing floats free during the sleep-wake cycle. Compartments lock, straps secure, and labels remind. Everything has its place. It is an environment designed to be predictable in an unpredictable setting. That predictability is a comfort. It is the engineering answer to the levity of floating objects. Consider, too, the many redundant systems quietly built into the station. There are backups for power, multiple routes for data and communications, and fail-safe mechanisms for atmospheric control. The engineers design with humility, multiple lines of defense for the things we almost never need but could not live without. Redundancy is not laziness, it is foresight. It is the careful practice of preparing for the reappearance of gravity at launch and re-entry, for micrometeorite impacts, for power fluctuations. The station's calm exterior masks a layered resilience that lets curiosity flourish. Now, let us lift our eyes from the humming modules and move outward, where gravity writes a much longer story. If microgravity invites us to rethink the familiar, the cosmos invites us to appreciate scale. There is a tidy line connecting the physics of the pen that drifts beside you in orbit to the slow, patient contraction of a cold cloud of gas that will one day ignite as a star. Both situations are governed by gravity's character, though their language and tempo differ. Think of a molecular cloud, diffuse, cold, enormous. Most of the gas sits idle for eons, held in the gentle balance between its internal pressure and the pull of its own gravity. Yet imperfections, a denser pocket here, a whisper of shock from a nearby supernova there, can tip a region into collapse. Gravity gathers material inward, compressing and heating it. When temperature and pressure reach critical thresholds, nuclear fusion starts and a new star is born. The process is majestic because it unfolds over tens of thousands to millions of years, patient and inexorable. Gravity is not a hammer so much as a slow hand that coses structure out of chaos. On the scale of galaxies, gravity becomes a sculptor of beautiful complexity. Observe a spiral galaxy and you perceive sweeping arms of stars, gas, and dust rotating in a coherent dance.
Yet, when astronomers measured the speeds of stars far from the galactic center, they found a puzzle. The stars were moving faster than the visible matter alone could account for. The simplest explanation was that there must be more mass than meets the eye, gravitationally binding the outskirts. This unseen influence is what we term dark matter. We do not know its nature for certain, but we infer its presence from how gravity appears to behave on those scales. Dark matter is an example of how gravity can act as a detective. It tells us about the presence of something even when that something refuses to shine. Gravitational lensing is another way gravity reveals itself as an observational tool. Massive objects like galaxies or clusters warp the path of light that passes nearby, magnifying and distorting the images of objects beyond them. It is as if the universe holds a set of natural magnifying glasses. Astronomers use these lenses to study distant galaxies, to weigh mass distributions in clusters, and to peer deeper into the cosmos than telescopes alone would allow. The technique elegantly unites the geometric picture of gravity with practical observation. On vaster cosmic scales, gravitational attraction has helped shape a cosmic web, filaments of galaxies and clusters interleaved with vast voids. Simulations that begin with the fluctuations seen in the cosmic microwave background and let gravity run its course produce a network that strikingly resembles observed large-scale structure. Gravity works quietly across billions of years, clustering matter where fluctuations permit and leaving emptiness where they do not. But gravity also has wild, extreme faces. Near massive compact objects, black holes, space-time curves so steeply that familiar intuitions break down. The term black hole conjures powerful images, but it's useful to keep the science calm and literal. A black hole is a region where space-time curvature becomes so intense that within a boundary called the event horizon, not even light can escape. Around such objects, time and space swap roles in a sense that boggles the mind. Clocks tick differently, orbits behave strangely, and light itself can be trapped or flung outward after a dramatic detour.
We have direct evidence of these extreme dynamics. The first direct detection of gravitational waves in 2015 by the LIGO Observatory confirmed a vivid prediction of general relativity. Accelerating masses, especially in violent mergers of compact objects like black holes or neutron stars, generate ripples in spacetime that travel outward at the speed of light. Those ripples arrived at detectors on Earth as minute changes in arm length, changes far smaller than a proton, yet they were measurable. That discovery opened a new sense. We can now listen to the universe as well as see it. Gravitational wave astronomy has since given us a catalogue of cosmic collisions, each one a quiet but intimate herald of extreme gravity.
Time dilation is another striking consequence of Einstein's view. Clocks in stronger gravitational fields tick more slowly relative to clocks in weaker fields. That is not a poetic claim, but a physical one. It is measured and used. Satellites that orbit the Earth and carry precise clocks must have their time corrected for both their orbital speed and the slightly weaker gravity they experience compared to the Earth's surface. Without these adjustments, technologies like GPS would lose their accuracy rapidly. Close to very massive bodies, this effect becomes dramatic. If you were to hover near the edge of a sufficiently strong gravity well, your clock would run noticeably slower compared to someone far away. The image is strange and intimate. Gravity can stretch not only space, but the rate at which events pass. The study of black holes moved from the realm of thought experiment into observability with the imaging of a black hole's shadow by the Event Horizon Telescope. That image and the following observations are not cinematic in a sensational way. They are precise, patient measurements that confirm centuries of inference about the power of gravity to concentrate mass and to bend light. We have reached a stage where the quiet predictions of theory meet the noisy complexity of reality and yield a deeper understanding. As we edge towards the frontier of physics, we find room for hypothesis and for respectful uncertainty. There are carefully fashioned ideas that attempt to explain phenomena like dark matter and dark energy in new ways. One class of proposals suggests that gravity might not be fundamental, but emergent, something that arises from the statistical behavior of microscopic degrees of freedom, much in the way thermodynamic temperature arises from molecular agitation. Another line of thought uses the holographic principle, a suggestion that the information content of a region of space can be encoded on its boundary, somewhat as a three-dimensional image can be encoded in a two-dimensional medium. These ideas are intellectually generous. They invite us to reframe old problems in novel languages. It is important to emphasize, gently and clearly, that such proposals are hypotheses. They are valuable because they push theoretical boundaries and propose testable differences, but they are not yet established fact. Some models make predictions that can be compared to observations, others remain speculative. The right attitude is curiosity with caution, an openness to the idea that our current vocabulary might be incomplete, paired with a rigorous demand for evidence. One of the things floating in microgravity teaches us about these abstract ideas is methodological. When you remove a commonly held constraint, like the constant downward force we take for granted, you are forced to separate what is essential from what is environmental.
In the same way, when theorists contemplate that gravity might be an emergent phenomenon, they are asking which features of gravitational interaction are universal and which are dependent on a deeper substrate. That line of thought has led to useful cross-fertilization between statistical physics, quantum information theory, and gravity research. The labors are subtle, the mathematics dense in places, and the hypotheses are measured. From the vantage of a sleeping mind, they are invitations to imagine rather than pronouncements. There is a wholesome symmetry in how practical lessons from life in orbit can inform abstract cosmological thinking. Microgravity experiments let scientists study fluid behavior, combustion, crystallization, and biological responses in the absence of a dominant gravity vector. The results can reveal hidden dependencies and boundary conditions for our terrestrial intuitions. Those experimental insights, in turn, feed back into models of planet formation, the behavior of accretion disks around young stars, and even the microphysics that might influence large-scale dynamics. Science is conversational. Experiment and theory talk to one another, often in low, careful tones. Before we close, it is worth dwelling on a couple of quietly beautiful examples that stitch the domestic with the cosmic. One is the behavior of flames. On Earth, convection, hot air rising, dominates the shape of a flame. In microgravity, flames become spherical, soot patterns change, and diffusion becomes the principal driver of reaction. These behaviors teach combustion scientists about low-oxygen environments and can influence attempts to model fires in enclosed spaces on Earth. The lesson is small and practical, but it is also poetic. The absence of a directional pull reveals symmetries otherwise hidden.
Another is the formation of crystals. In the calm of microgravity, crystals can grow larger and more perfect than on Earth, untroubled by sedimentation. Protein crystals grown in space have been studied with hopes of understanding molecular structures more precisely, sometimes informing pharmaceutical research. Again, this is an example where the altered environment acts as an experimental scalpel, exposing features that a gravity-rich setting would obscure. As we let these images settle, consider the human habit of translating wonder into stewardship. Astronauts returning from long missions often speak about a changed sense of responsibility, a clearer sense that Earth is fragile and that the large sweep of human activity leaves a detectable mark. Seeing the planet as a finite, luminous object evokes a humility that can shape policy, conservation, and care. Gravity, in its quiet way, ties that sense of connection together. It holds us near enough to see one another clearly and to feel the weight of mutual obligation.
Now, as we bring this voyage to its bedside conclusion, return to the image that began our journey, your room, a soft capsule circling a pale blue marble. Let the paradox sit with you again. In floating, we reveal gravity's hand. In the absence of the floor, we notice the architecture of dependence that gravity has carved into life and into the cosmos. The experience of microgravity is not an escape from gravity's truth. It is a lens that sharpens our understanding of how gravity operates, from apples to galaxies, from tumbling pens to the gentle ripples of space-time itself. Breathe in. Feel the air move, subtle and steady. Breathe out. Let the sense of curiosity and calm find its rest. If tonight your mind wanders back to the station, imagine the quiet fans, the soft clank of a Velcro strip, the tethered sleeping bag snug against its wall. Imagine astronomers listening to the universe's faint thrum, and engineers tuning a pump so you can sip water that yesterday may have been part of a plant. These are small acts of care that allow vast curiosity to persist. If this night's voyage has felt like good company, it would be lovely to hear from you. In the comments, tell me where you're listening from and what time it is there. There is a quiet comfort in knowing we are drifting together from many different time zones. And if you'd like to make these gentle voyages a regular part of your evenings, consider subscribing. There will be more calm explorations to come. For now, let your thoughts orbit slowly, like a station circling a day-lit curve of Earth. Let the questions that stirred you settle into the soft dust of sleep, and let the knowledge that gravity is both familiar and mysterious keep you company as you drift. Good night, and may your dreams carry the quiet wonder of the universe.